Welcome to Lecture 3, 3D vectors, position vectors, and vector along a line. The first thing we'll do is establish the 3D coordinate system that we'll be using throughout the course. Then we'll talk about the rectangular components of a 3D vector, Cartesian unit vectors in 3D, 3D Cartesian vectors and how to add them. And then we'll talk about position vectors and a force vector directed along a line. We'll be using what's known as a right-handed coordinate system for our 3D work throughout this course. You can check to see if a given coordinate system is right-handed by doing the following. Using your right hand, extend your fingers out along the x-axis such that they can be curled into the y-axis. When you curl your fingers into the y-axis, if your right thumb points along the direction of the positive z-axis, then it is a right-handed coordinate system. Let's look at several 3D coordinate systems and use the right-hand rule to check and see if they are right-handed or not. The first one here, if I, using my right hand, extend my fingers down the positive x-axis such that I can curl them into the y-axis, my thumb will point down the z-axis. So that is a right-handed coordinate system. The second example here, I'm going to position my right hand so that my fingers point along the positive x-axis such that I can curl them into the y-axis, and again my thumb is going to point in the direction of the positive z-axis when I curl my fingers. This third example here, it's a little harder to get your hand into this position if you're trying to do this as we go along. But if I position my right hand with my fingers going along the positive x-axis such that I can curl them into the y-axis, you will find that your thumb does point down along the positive z-axis. So this is also a right-handed coordinate system. The final example here, now I'm going to point my right fingers down the positive x-axis. When I curl them to the positive y-axis, my thumb is now going to point this way, not along the positive z-axis. So this one is not a right-handed coordinate system. The right-handed coordinate system that we're going to be using throughout the course will be one where the vertical axis is going to be our z-axis. The horizontal axis is our y-axis. And the third axis is going to be our x-axis. Now remember, it's always a challenge to express and visualize a 3D world when we're looking at a flat screen or a flat piece of paper. So remember that the x-axis is coming out at a right angle to the screen or the paper. But if we drew it that way, we would see just a point. It would just come straight out at us. We wouldn't see any line for the axis. So remember that the angle between the y and the z axis is a right angle, as is the angle between the x and the y axis, as is the angle between the z and the x axis. So keep this in mind when you're doing 3D work. Let's look at the vector A that's here in the 3D space that we've created, and we want to resolve A into its three components, its x, y, and z components. So this is going to be a two-step process. First, we're going to resolve A into a component that exists in the xy plane. We're going to call that A prime. And its second component will be its component along the z-axis, which we're going to call A sub z. So this is nothing different than we did when we were working in 2D. Remember that this is a rectangle here. These are all right angles. So A prime and A sub z are just the rectangular components of A. Now we're looking for A sub z, so we're not going to do anything else with that, but A prime, the vector A prime, needs to be broken down into two components along the x and the y axis. In other words, we're going to now break A prime down into its rectangular components in the xy plane. So again, remember that these are right angles, and A prime's components are its rectangular components along the x and y axes, or ax plus ay. Now we can substitute in ax and plus ay for A prime and end up with A, the vector A, can be written as its x, y, and z, or Cartesian components, ax plus ay plus az. We're going to make use of Cartesian unit vectors in 3D, just like we did in 2D. So we have I, which is the unit vector along the positive x-axis. J is the unit vector along the positive y-axis. And now we add K, which is the unit vector along the positive z-axis. So using I, J, and K, we can now write the vector A in Cartesian form. So A can be written as the magnitude of A sub x times the unit vector I plus the magnitude of A sub y times the unit vector j plus the magnitude of A sub z times the unit vector k. The magnitude of our original vector A is going to be equal to the square root of the sum of the squares of the magnitudes of the components of A. This is very similar to what we did with 2D vectors. We've just added that third dimension now. The direction of A is defined by three angles. The angle between the x-axis in A, which we call alpha, the angle between the y-axis in A, which we call beta, and the angle between the z-axis and A, which we call gamma. These are known as the coordinate direction angles of A. The cosines of the coordinate direction angles can be expressed as follows. The cosine of alpha is equal to the magnitude of the x component of A divided by the magnitude of A. The cosine of beta is equal to the magnitude of the y component of A divided by the magnitude of A. And the cosine of gamma is given by the magnitude of the z component of A divided by the magnitude of A. These are known as the direction cosines of A. And from the picture we're working with here, they're not necessarily intuitive that these represent the cosines of those angles. Probably the easiest one to see is the cosine of gamma. Remember, here's gamma here. Okay. Gamma is from the z-axis to A. And it helps to remember that this is a right angle here. Okay. So if you look at the triangle now that contains that right angle, and given the position of gamma, the cosine of gamma is equal to this side, which is the magnitude of the z component of A, over the hypotenuse, which is just the magnitude of A. With the direction cosines, we can define a unit vector in the direction of A that we'll call u sub A, where u sub A equals the cosine of alpha I plus the cosine of beta j plus the cosine of gamma k. Now, if we can write a unit vector in the direction of A, and we know the magnitude of A, then we can express A in Cartesian form by this equation here, where vector A equals the magnitude of A times the unit vector in the direction of A. So this is one method. If we know the coordinate direction angles or the direction cosines, this is one way we can express, one method we can use to express a given vector in its Cartesian form, which we can then use for Cartesian vector addition, which we're going to talk about on the next slide. One other thing, since the magnitude of any unit vector is 1, then we can write this equation where the cosine of alpha squared plus the cosine of beta squared plus the cosine of gamma squared equals 1. And this again is related to the Pythagorean theorem. Now, so this allows us to calculate an unknown angle. If we know two of the angles associated with the vector or two of the direction cosines associated with the vector, we can calculate the third using this equation. Let's look now at the addition of Cartesian vectors. We just discussed one method for expressing an individual vector in 3D space in terms of its Cartesian components, or expressing it in Cartesian form. There are other ways. We're going to look at another popular method a couple slides ahead. But for now, let's assume that we have our individual vectors written in Cartesian form, and we want to add them together to find the resultant of those vectors. So it turns out that this process is pretty easy, although it can be tedious. A lot of bookkeeping, minus signs, etc. But it's basically the same as we used when we added 2D vectors that were expressed in Cartesian form together. So let's consider two vectors, A and B, in 3D space that are expressed in Cartesian form in terms of I, J, and K to discuss this. The resultant of A and B can be written here, no different from our 2D equation, and we're going to calculate that resultant by adding all the I terms of the individual vectors together. In this case, we just have A and B, adding all the J terms of the individual vectors together, and adding all the K terms of the individual vectors together. So really no different than our 2D process. We just added this third dimension here. Okay, so in general, if we have a system of concurrent forces, again, the forces have to be concurrent. We're going to learn how to deal with non-concurrent forces later in the course. And this is for any number of concurrent forces. The force resultant, F sub r, can be written as the sum of the forces. In other words, if we had 5 forces, A, B, C, D, E, we would just write a vector equation, A plus B plus C plus D plus E, and then we would put all of those forces into Cartesian form and just sum all the I components, all the J components, and all the K components. Before we look at another method to express a vector in 3D space in Cartesian form, we need to introduce position vectors. A position vector is a fixed vector that locates a point in space relative to another point. So let's consider 2 points, points A and B in 3D space. And they have the 3D coordinates of A, X sub A, Y sub A, Z sub A, and B has the coordinates X sub B, Y sub B, and Z sub B. Then the position vector from A to B is given by, and we call our position vectors R, little r. That position vector is given in Cartesian form by X sub B minus X sub A, I, Y sub B minus Y sub A, J, plus z sub b minus z sub a k. Now what is that physically speaking? It says that if you start at point A, you need to go x sub b minus x sub a in the I direction. Then you go y sub b minus y sub a in the j direction. And then you go z sub b minus z sub a in the k direction, and you end up at point B. So we're going to make use of the position vector in the case where we have a force in 3D space where the direction of the force can be defined by 2 points located on its line of action. So we don't know the coordinate direction angles of the force, we don't know the direction cosines of the force, but we do know 2 points located along its line of action. This method of expressing a force in 3D space in Cartesian form is known as force vector directed along a line. Let's look at the situation in the figure here. We have a chain connected to a wall at point A, and at the other end of the chain, point B, we're applying a force F. Note that the line of action of the force is collinear to the chain itself. In situations like this, where whether it be a chain, a cable, a rope, we have a 3-step process that allows us to determine the force in terms of a Cartesian force vector. The first step being finding the position vector r between points A and B. It's labeled on the figure here, but we really want to get in the habit of being a little more specific, and we're going to call that position vector r sub AB, signifying that it's from A to B. Notice that r has to be in the same direction as the force is acting. And in future problems, you may have multiple forces, each with their own position vectors, and it's going to get confusing if you don't have a specific name for each individual position vector. Okay, and this is a vector, so I should put a little arrow over that. The second step is going to be to find the unit vector, which we'll call u sub AB. Again, we need to make sure that we're keeping track of the individual unit vectors, position vectors in problems where we have multiple things going on. And we can express that unit vector by this equation here, where that unit vector in the direction of AB equals the position vector from A to B with the position vector's magnitude divided out of it. In other words, we have a position vector that has magnitude and direction, and if we divide out its magnitude, we're left with a unit vector, a vector that has a magnitude of 1 in the direction of RAB. And to find r, we're going to make use of the Pythagorean theorem again, where r is defined by this equation here, which is just the square root of the sum of the squares of the x distance, the y distance, and the z distance that was required to get from A to B. Once we know the unit vector u sub AB, which will be in Cartesian form, we can write f in Cartesian form by taking the magnitude of f and multiplying it by u sub AB.